Hello and welcome back. In this video we're covering section 5.3 on what's called the quotient rule for exponents. So far we've seen a few rules with exponents. Just to kind of summarize here. If we have something like a to some power m times that same base to some power n, we end up adding the two exponents together. This can be viewed as a to the power of m plus n. We've seen if we raise a power to another power, so a to the power m raised to the power n, this results in the multiplication of these two exponents. And then we've also seen that if we have some fraction, a over b raised to the power n, we can effectively distribute this a to the power n over b to the power n. We've seen something similar if we have a multiplication, a times b to the power of n. This distributes to each term, a to the power n times b to the power n. We've seen raising something to the power of 0, as long as the base is not equal to 0, that gives you just 1. And if you have a negative exponent, let's say negative n, this ends up flipping a fraction, or if you just have a single term like this, it puts it in the denominator of a fraction with the positive exponent. So let's complete our list of rules today with what's called the quotient rule. And this is when we have something raised to some power divided by that same base raised to another power. When we had this with multiplication, like a to the power m times a to the power n, we ended up adding these exponents together. And so it kind of follows along the same line of logic that division would end up with a subtraction of these exponents, m minus n. So just to give a quick example, let's say we have a to the fifth power divided by a to the third power. So just following this rule, we would subtract the exponents and get a to the second power. But if we view this as doing some cancellation, hopefully this can make a little more sense. We effectively have 5 a's on the numerator. So a times itself 5 times. And we have 3 of them on the denominator. And since everything is multiplied, we can cancel, say, this a with this a, this a with this a, this a with this a, and then we're left with 2 at the end. So a squared, which is effectively a to the power of 5 minus 3. So when we're subtracting, we're really dealing with this cancellation that's happening. And you might cancel everything from the denominator, or if this was flipped, if it was, say, a cubed over a to the fifth power. In one sense, we can see all 3 of those a's on the numerator canceling with 3 in the denominator. So you would have 2 left in the denominator, which, based off of our rule with negative exponents, we could write as a to the minus 2 power, which you would get by taking 3 and subtracting the 5. So just to show a couple different approaches to try to make this rule make sense. But overall, you can just apply this subtraction rule when dividing the same, you have the same base on the numerator and denominator and 2 different exponents. So let's go through a few specific examples here. So part A, we have 2 to the 9th divided by 2 cubed. So the base is the same. So we can write this as 2 to the power of 9 minus 3, or 2 to the 6th power, which is equal to 64. In part B, we have t to the 10th over t to the 4th power. So we can write this as t to the 10 minus 4 power, or t to the 6th. Or we could view 4 of these are canceling with 4 of those in the numerator. We would have 6 left over. In part C, we have 3 over 3 to the minus 2 power. Starting to get a little bit tricky here, but let's just stick with this rule, and we can view the 3 on the numerator as 3 to the first power. So that means we can write this as 3 to the 1 minus negative 2. Well, 1 minus negative 2, that becomes 1 plus 2. So 3 to the third power, which will give you 27. You can also view this, since this is a negative 2, it's actually going to like bring this up into the numerator and join with that 3. So we have 2 3's joining with the 1 3 in the numerator. Part D, we have n to the 5th divided by n to the 7th power. So let's just continue with this subtraction rule. This would be n to the power of 5 minus 7. 5 minus 7 is negative 2. So we can rewrite this as 1 over n squared. The negative power will put it in the denominator with a positive exponent. Or we could say these 5m's will cancel with 5n's in the denominator, and there will just be 2 left. There'll be none left in the numerator, so we end up with that 1. And then we have 2 left in the denominator. And then part E, we have 3 squared over 2 to the 4th power. So in this case, the bases aren't the same, so we can't apply one of these particular rules. We'll just have to evaluate this. 3 squared is 9. 2 to the 4th power is 16. So this rule only applies when the bases are the same, and that's what we had with our 4 previous examples here. So let's apply this to variables as well, maybe some more complicated expressions. So you might find this in the middle of some bigger algebra problem. We might end up with something messy like this. X to the 8th times y to the 7th over x cubed times y to the 4th. So we have 2 different variables and then some mixture of exponents. We want to simplify this. So we can use the subtraction rule and say, well, this would be x to the 8 minus 3 power times y to the 7 minus 4 power. So 8 minus 3 is 5, and 7 minus 4 is 3. So 8 to the 5th times y cubed. Or we can see 3 of these being canceled and 4 of these being canceled. Part B, this one's extra messy. So 12 times a to the minus 5 power times b to the 10th power over 8 times a to the minus 3 power times b squared. It's kind of harder to see based off of that cancellation rule. We have these like negative exponents involved, so let's just follow with this subtraction rule. And everything's multiplied, so this 12 over 8 I would separate out in front, and we can reduce that in a second. And then we have a to the power of negative 5 minus negative 3. Just got to be careful with this double negative. And then times b to the 10 minus 2 power. That one's a little bit nicer. So 12 over 8, we can divide both of those by 4. 4 goes into 12 3 times, goes into 8 2 times. And then negative 5 minus negative 3, that's like negative 5 plus 3. So we get a to the minus 2 power. And then times b to the 8th power. And since a has a negative power, we can end up placing it down in the denominator of this fraction. B has a positive power, so we can place that in the numerator of this fraction. So we can condense this down a little bit more into 3 times b to the 8th power over 2a squared. And I think that's all the examples for this section. Yeah, so we're just really practicing this rule. If we have a division with 2 different powers, we can write it as a subtraction. That will complete our set of exponent rules for now. All right, so let's add it to our list here. If we have a to some power m over a to some power n, we can write that as a to the power of m minus n. Okay, that's it for this video, and I'll see you next time.